All right, awesome. Thank you, everyone. My name is Jacob Zelko, and we're kicking off the first ever Julia Health mini symposium. I'm the Julia Health leader, and I'm excited to introduce Kavya, Subramanain. I'll let you go ahead and get set up, Kavya, but this will be having a variety of talks today, just as we're going through kind of the mini symposium. So feel free to stay tuned and hopefully learn some about how Julia can be used in a variety of different health research and applications. Thank you.
Good morning, everyone. My name is Kavya, and I am an undergraduate at Boston University. I'm currently a rising junior, and along with the team at Visuora AI Labs, I have been working on an adaptive tumor growth forecasting model via neural and universal ODEs. And today, I'm really excited to share more about my research with you in this talk. So I'll be covering the following. I'll firstly briefly introduce the problem, talk about the motivation behind it, then talk about the existing models that exist, and then dive into the methodology, results, and so forth. So I'd like to begin by talking a bit about the motivation behind this problem. Cancer remains one of the leading causes of death globally, and there's projected to be over 2 million cancer cases and more than 600,000 deaths this year in the US alone. In this context, it becomes incredibly important to accurately predict how a tumor grows over time, as this not only helps doctors to effectively plan treatment, but it ultimately helps in saving lives. And therefore, this problem is not just a theoretical exercise, but rather it has the potential to impact human lives. But let's take a step back for a moment. What makes tumor growth modeling so difficult? What are the challenges? Well, there's several. To begin with, tumors are incredibly complex. There's differences not only across various patients, but also within the cells of the same tumor. So this poses a very, very tough challenge to solve. Besides that, there's the differences in immune system responses when a patient is exposed to radiation or other kinds of therapy. Additionally, we've also got the environmental as well as external factors that influence tumor growth, whether it's the tumor microenvironment, right from the availability of oxygen or nutrients, as well as the surrounding tissue and their stiffness and so forth. Also, environmental factors such as a person's diet or the kind of therapy that they're undergoing can have a huge impact in the way a tumor progresses over time. And from a purely modeling standpoint, there's also the problem of having limited experimental data with very sparse time points. So all of these challenges put together make tumor growth modeling and forecasting a very critical challenge. I'd now like to touch a bit on the existing models for tumor dynamics and forecasting. So firstly, we've got the ordinary differential equation-based models, such as the Gompertz or the Bertalanffy equations. One big strength is that they're computationally efficient. It's very easy to work with. However, due to the fixed parameters, it makes it really difficult for the model to adapt with patient-specific variability. Similarly, for partial differential equation-based models, although they include that additional spatial resolution, it can still be quite hard to personalize it to a specific patient. And finally, more recently, there have been quite a few machine learning models that have come forth. However, they do lack the biological interpretability of the more mechanistic models, despite being able to capture the more complex nonlinear dynamics of tumor growth. So as you can see, every model has its own strengths and it contributes something important. However, none of them really provides us the interpretability as well as the adaptability that's required for biological modeling. And Hence, we would like to propose a scientific machine learning-based approach to tumor growth modeling. Scientific machine learning combines the power of traditional ODEs with the adaptability of neural networks. This allows the model to learn directly from experimental data by replacing fixed parameters with neural networks. So essentially, we're able to retain the mechanistic interpretability of the ODE and PDE models, while at the same time being able to get the flexibility of a pure machine learning model. And therefore, as you can see in the Venn diagram, we get the best of both worlds. All right, so now I would just like to talk a bit about our experiment and the data that we've used. So we chose an experimental data set of breast tumor growth in animal models. These were measurements of tumor volume in cubic millimeters over the time span of a few days. As you can see in the graph, the data followed a sigmoid-like growth pattern, which is very characteristic of typical tumor growth. It starts off kind of slow, and then in the middle, it rapidly accelerates, and finally, it reaches a maximum volume or a carrying capacity where the graph starts to plateau. So in order to get a smooth approximation, we applied a sigmoid-based interpolation to the data, which was able to capture the general trend without fitting to the noise in the data. And then for our base model, we chose the Gompertz ODE equation. It is a sigmoidal growth model that was originally proposed in 1825 to describe human mortality. It wasn't until the 1960s, though, when it was first used to model tumor growth. But since then, it's come a long way and has been widely adopted in both the biological as well as the medical sciences for tumor modeling. And there's several research papers that have assessed the benefits and limitations of the Gompertz ODE as well as a lot of other ODEs. As you can see, the equation mainly has a parameter called the intrinsic growth rate, represented by A, and it's multiplied by the volume as well as the log of the carrying capacity divided by the volume. All right, so we then used the DifferentialEquations.jl package to define the ODE problem with the following parameters, and then solved it using the TSET5 solver. This produced the following result. As you can see, the Gompertz growth is not able to capture the intricacies of the experimental data, and that's where we come in, and we have proposed a neural ODE-based solution, as well as a UDE-based solution. Let's first dive into neural ODEs. What are neural ODEs? Well, they're a family of deep neural network models that replace the fixed parameters in the ODE with a neural network. This allows us to flexibly model continuous time dynamics using a continuous transformation to update the hidden states like so. And essentially, as I mentioned, we replaced the fixed ODE parameters with a trainable neural network. We inputted volume as well as time as inputs, and the network has 3 hidden layers with the tanh activation function and the following number of neurons per layer. We also normalized our input data and defined our neural ODE function and subsequently solved it using the TSET5 solver. Finally, we went ahead and optimized our solution using the Adam optimizer. We experimented with a bunch of learning rates and iterations, and the best result was obtained using these parameters. So here is the result of our neural ODE. As you can see, the solution agrees strongly with the experimental data, and it's able to effectively capture the sigmoid-like growth of the tumor, and it's a big, big step ahead from just the traditional Gompertz ODE model. Finally, we took it a step ahead and decided to forecast future tumor growth using our neural ODE model. We started off by training it on 100% of our data, and then forecasted beyond the time span from a range of 32 to 40 days. As you can see, the neural ODE was able to capture that plateauing nature of the tumor growth, and we also went ahead and forecasted with different data ratios. So a train test split of 90-10 as well as 80-20 gave us a really, really good forecast. However, we did notice that at about the 70-30 data split is where there was some deviation from the experimental data. I will be talking about this a little more, but as a next step, we will be performing further hyperparameter tuning in order to reduce this error. Finally, I would like to talk about the universal differential equations. So UDEs combine differential equations with neural networks that allows them to model systems with unknown or partially known dynamics. What makes them different from neural ODEs, though, is that we are replacing just the key interaction terms with neural networks rather than replacing the entire equation. So as you can see here in our example, we are replacing the growth rate A with one neural network and the log term with another neural network. So as I mentioned, we replace the key interaction terms in the ODE, and we feed in the volume and time as input as earlier. Each of the networks has two hidden layers with the tanh activation function, and the input data is also normalized to ensure that there's stable training. Finally, we define the UDE function and solve it using the TRBDF2 solver. And we optimized it using the Adam optimizer, but in this case, we had a three-stage optimization approach with these learning rates. So here are the results for our UDE model. Again, similar to the neural ODE, the UDE was able to capture the sigmoidal growth of the tumor data, and it strongly agreed with the real-world experimental data that we used for training. Then, similar to the neural ODEs again, we forecasted using 100% of our data. And as you can see, it does a decent job of capturing that plateauing nature again. We also forecasted with different data ratios, starting with a 90% training and a 10% forecast. As you can see, the green line overlaps the orange dotted line pretty well. And even at the 80-20 split, it still manages to capture that slowing down pattern. But again, at the 70-30 split is when it started deviating from the data. But we hope to further improve this as this is an ongoing research. We will be performing further hyperparameter tuning to ensure that this result is improved. So our neural ODE and UDE models were able to accurately capture the sigmoidal growth curve of tumor growth, and compared to traditional models like the Gompertz ODE. They were also able to adapt to the nonlinearities in the tumor data by replacing the fixed terms with trainable and flexible neural networks. And finally, our approach also retains interpretability by grounding the neural network in biologically meaningful ODE framework. So this allows us to make inferences from our data, which are grounded in which are backed by scientific meaning. We use several Julia packages in our research, and it significantly helped us model these complex dynamics and made it much easier to work with these complex tools like neural ODEs and UDEs. The DifferentialEquations.jl package, the DiffEqFlux, the Optimization.jl, Lux, and so on form the core Julia SciML ecosystem. And we were able to harness its power to make the most of our modeling. I would just like to talk briefly about some of our next steps. As I mentioned, this is still an ongoing research, and we hope to improve our forecasting further by using more hyperparameter tuning techniques. We would also like to determine the forecasting breakdown point for both our neural ODE as well as our UDE model. Also, we only applied this to a specific data set. So in order to evaluate how generalizable our models are, we would like to apply it to more data sets. And also, we intend to make our tools open source after publication and upload all of our code on GitHub. So to conclude, tumor growth is an incredibly complex process, and it's influenced by several factors that makes it a challenge to model and forecast. And traditional models that are based on ODEs or PDEs have limited flexibility because of their fixed parameters. And pure ML models, due to the black box nature of machine learning, don't provide the interpretability that the more mechanistic models have. Hence, we are working at the intersection of both these kinds of models and applying powerful scientific machine learning frameworks, including tools like neural ODEs and UDEs that learn these tumor dynamics directly from experimental data. Our models are not only able to capture the sigmoidal growth pattern of tumors, but they're also able to effectively forecast future growth using just limited data. Finally, to close, I would just like to bring us back to the bigger picture here. Our work shows that by combining scientific machine learning with traditional modeling, we are not only able to improve predictive accuracy, but it also brings us closer to a more data-driven personalization of cancer care. But more importantly, this is not just about a mathematical or a computational exercise. It's a critical tool that helps doctors in decision-making, treatment planning, and also improving patient outcomes. We're taking a step closer to precision medicine, particularly in oncology, and create models that don't just simulate tumor growth, but rather carry the potential to save lives. Thank you so much for listening.
Awesome. Thank you so much. Thank you to our speaker. We have time for plenty of questions right now, so if anyone has any questions, I will run you the microphone. Floor is open.
How many of these curves do you have, like in your? Yeah, I'm sorry. How many of these curves do you have for all the different clients, for all the different patients?
So right now we're using an experimental data set that's based on animal models. So these are mice injected with like tumors.
Okay.
So.
All right, but like how many of these curves, like in your data sets, how many of them are there?
You mean the data points in the
Well,
experimental?
not like, I mean, is it like just one curve that you have, or do you have like many mice that had many cancers?
Yeah, so there's multiple mice. We chose a particular one which had about 6 to 7 data points, and then hence we had to apply the interpolation to get a smooth approximation for our ground truth data.
Okay. Have you considered using embeddings for, like, because you've got, basically, it's like you've got each mouse is going to have like a different parameter in the way, but like they all follow basically the same sigmoid-ish curve, right?
Yes.
So if you had like embeddings, then you could have that like this mice is like slope is like this much, and the next mice slope is like that much, and so on.
We haven't considered that yet, but I'd definitely love to like talk more about that and like potentially apply that.
Okay. All right.
Thank
Thank
you
you very much.
Thanks a lot.
Hi. Just to clarify, I think the earlier question was how many different trajectories did you train the neural ODE on? It appears that it was only one. I mean, one curve did have 6 points, but the number of curves that you trained on was only one.
Yes, that's right. As of
Cool.
now, yes.
And then earlier also you mentioned that the definition of a neural ODE is based on replacing the fixed parameters of the equation, but actually what you're doing is you're replacing the right-hand side entirely, not just the parameters.
Yeah, yeah.
And later on also, you mentioned that you foresee expected improvement through the tuning of hyperparameters for the neural ODE in the sense of forecasting, which is, I guess you could call extrapolation, but it's unclear how that would bear any fruit given that in order for you to be able to extrapolate, you have to learn something about the underlying dynamics, and just simply changing the layer size or the number of hidden nodes won't necessarily meaningfully try and address that directly. It'll be more like rolling the dice and hopefully something would do better. So I'm curious about what the actual strategy is to improve the dynamics outside of kind of twiddling knobs and hoping that there's some outcome.
So we definitely want to train our neural ODE model on multiple data sets. So as I mentioned, this was on a particular model. So having that, like sort of that generalizability would help us achieve, as you said, it will be able to learn the dynamics itself.
Cool, thanks.
So our question over here.
Hi, thank you for the great talk, very enthusiastic. I'm just curious about how you thought about, first of all, like changing the differential equation, because you use this, I forgot the name, like
Gompertz.
Yeah, model, but like a hyperbolic tangent function is a classical solution of any other differential equation. Have you thought about probably changing that instead of doing, that's my first question. And then second, you mentioned that you have a lot of different mice data set. Do they all follow a sigmoidal function?
Yes, so firstly, to address the first question, so we just chose the Gompertz ODE because it is one of the most widely used ODE models for tumor growth. But you're absolutely right. There's multiple ODE as well as PDE models that we will explore as one of the next steps. For example, there's the logistic equation, the exponential, the Bertalanffy, and so on. So those can also definitely be utilized for training our neural ODE as well as our UDE. As far as the second question goes, so I'm sorry, could you please?
Oh yeah, like if all of them follow a sigmoidal function.
Yeah, yes. So generally, we did notice that the volumes did follow a sigmoidal growth. So yeah.
Okay, just slightly. You said that you have once you reach, steady state, or I mean like the saturation point, some of them start to grow. Do you think that's a numerical artifact, or does it have a physical meaning? Like tumors, I believe tumors can grow even beyond that, right?
Yeah, potentially. So as you said, that it could be possible that our models are able to capture those intricacies and potentially are sort of implying that it's not reached the carrying capacity yet. So that could be a reason, but we're yet to explore that. So hopefully we're able to find. Yeah, absolutely.
Okay, any more questions? I think we have time for maybe one more. Okay.
Yeah, nice talk. I just have one thought and then a question. Actually, about the question that was just asked, the first one. I've worked a little bit with them before, Neural ODEs, and my thought on like using a different, like you use the Gompertz. My thought was always find like a mechanistic model that sort of fits the data pretty well, and then I think the point is that then modeling those mechanistic parameters with like the neural network, like you said, introduces the flexibility, and the shortcoming of the mechanistic model is not that the model's bad, but that the parameters just aren't flexible. So I was just, that's an opinion I've held, so I'm wondering what you or maybe anybody else in the room thinks about that, for one. And then I forgot the second thing I was going to say, so I'll let you guys go.
Yeah, I mean, that's definitely quite interesting. I mean, I have only started working in the SciML space for the last couple months, but as far as I know, based on my knowledge, I feel like it's like, I guess like changing the models might help, but again, it just depends on the way it's trained, and perhaps even using better data might help.
If we can be quick.
Okay. The second thing, I guess, was have you looked into modeling like interventions, like at some given time point in like the middle of like the time course of neural ODE or of the tumor growth or something like that?
So just to clarify, what exactly do you mean by interventions? So as in the...
Like a therapy, for example,
Right.
cut the tumor size in half.
Yeah, yeah. So that's definitely one of the things that we did set out to explore. And as I said, this is ongoing research. So we will certainly look at the effect of radiation, for example, or you know, various things like maybe changes in diet and so on. So yeah, that would be one of the next steps for sure. But yeah, thanks for bringing that up.
Okay, why don't you all join me to thank our speaker once more for a wonderful talk. Thank you all so much for joining the first part of the Julia Health Mini Symposium. We're breaking right now. We'll be resuming after lunch break and a keynote following by Dr. Karandeep Singh. We'll be in the same room. We'll be picking up with Dr. Oscar Laverni talking about cock survival models. So hope to see you all very soon. Thank you so much.